Hey everyone! Welcome back. It's been a while since we did a lesson. So today we are switching gears. We are moving away from reviewing physical science and we're diving into earth science. Going all the way back to the beginning, looking at the beginning of Earth and Earth's evolution. So today's lesson is going to be all about discovery through fossils and how we can actually use fossils to help us put together some of the puzzle pieces of Earth's history. So everybody, what's our date today? April 16th, 2020. Our topic is discovery through fossils. We're looking at a 7th grade standard today. Explain and give examples of how physical evidence supports scientific theories that Earth has evolved over geologic time due to natural processes. Think about that word evolve. We talked about this when we went over evolution. What does that word mean? Our goal, I will be able to describe how fossils are dated and how they help to tell the age of rock layers around them. We got a few vocab words today: fossils, relative dating, absolute dating, law of superposition, faulting, folding, extrusion, intrusion, and index fossils. We are working towards answering our essential question: what methods allow scientists to tell the age of rocks, and what does this tell us about the Earth's history? This is ultimately what we're trying to find out. What does it tell us about Earth's history? That's our big picture. And our check for understanding today is we should be able to organize rock layers from oldest to youngest by looking at an image of them. So I'm about to show you a video that's going to show all of Earth's history in 1 single minute, 60 seconds. So as you guys are watching this, I want you to think about this question. How do we even know all of the events that they're showing actually happened, actually took place? So take a look and see. Alright, so what did you think after watching the video? A lot of y'all are probably thinking, Miss Hussein, that doesn't exist. There's no way we could even know that those things happened. And to a certain degree, you're right? When Earth was first formed, no human was there to record that and see it happen. So we don't really know for sure all the details. But we do have some idea of the history of Earth. We call this the geologic time scale. So again, remember we talked about geologic is anything to do with Earth. Really that first part, geo, is anything to do with Earth. Earth's time scale is the record of the life forms and geologic events in Earth's history. So make sure we're filling in our notes as we're going through. Scientists believe to have found evidence of materials that are 4.6 billion years old. Holy cow, that is old. And if we look down here on our image, we can see the beginning, 4.6 billion years old, all the way to most recent. There have been several key evolutionary periods: Paleozoic, Mesozoic, Cenozoic. We're not going to go into those details in this lesson, but it kind of gives you a cool idea of how Earth's history is mapped out. And these are all based on mass extinctions. So we see here is one extinction. This was another extinction. This is when the dinosaurs went extinct, between the Mesozoic and Cenozoic eras. So how did they actually know all of this happened? What did they use? If you said fossils, you are absolutely correct. Ding, ding, ding. So fossils are the physical remains of organisms, plants or animals, or any bacteria really, or an imprint of the physical remains. So an imprint is kind of something like this. It's not necessarily the skeleton itself, but it might be what the skeleton left behind. Fossils that are millions of years old can tell us about life on Earth long before humans were there. So we're going to look at how scientists actually use these to help them place events of Earth's history on a timeline. So how do we actually use these fossils to figure out how old the land was in the time that those organisms were alive? So there's two major ways we can think about it. There's relative dating and absolute dating. And I'm not talking about y'all's relationships. No, this is dating as in putting a date to a certain fossil. Okay? So I want you to think about these two statements. What is the difference between them? The first one says, I am older than my brother. And the second says, I am 14 years old. Pause the video, think about how they're different. Okay. So which one would you say is more of a guess, more of an estimate? If you said the first one, you're correct. This one is more relative. It's more of a guess. Whereas in the second one, I am 14 years old, that's telling you really directly what the age is. So this one is going to be the absolute age. Gives you an actual number. So whenever you're thinking about absolute, you have the actual number. So this relates to our ideas of relative versus absolute dating, because relative dating determines the age of rocks compared to the ages of other rocks. Not necessarily saying the exact number. Whereas absolute dating determines the number of years since a rock was formed. So if you see in this image over here, relative dating is mostly just saying is it younger, is it older, whereas absolute dating is giving us more concrete numbers to work with. So if I'm a paleontologist and I'm going and I'm in an archaeological dig, I'm digging up different fossils and I find 3 different fossils. Now I want to know, how old are they? When did these organisms even exist? Right? I can actually use these different methods of dating to figure out how old they are. And they both follow this basic law. The law of superposition. Superposition. So this law says that in horizontal layers of sedimentary rock, each layer is older than the layer above it and younger than the layer below it. Basically, it's saying that our oldest fossils are going to be found lower in the ground, and our younger fossils are going to be found higher in the ground. Think of it kind of like a pile of dirty laundry. Which is going to be the clothes you wore the longest time ago? Is it going to be up at the top or down at the bottom? Nice, down at the bottom. Those are the oldest ones. Then as the week goes on, you pile another one, you pile another one, you pile another. The ones at the very top are going to be the youngest or the newest. We can use that same idea to think about fossils, right? Whether we're thinking about relative dating or numerical dating, they both follow this law. That is just describing what is happening, right? Not necessarily explaining why, but describing what. So that's why we call it a law. So again, like we saw with folding and faulting, sometimes it's a little bit tricky to see exactly which rock layers are the older ones and which ones are the younger ones if they have all this movement in between or layers shifting, right? So the thing to know though is that things like extrusions, intrusions, and I'll take a moment to explain what those are. So an extrusion, you're thinking about lava that's coming from underground and actually flowing outward. It is external, like an extrusion. An intrusion, however, is lava that's underground, but it never really breaks the surface. It's just, it's created its own pocket and cools. So both of these, though, are newer than the surrounding rock. That surrounding rock was there much before those intrusions or those extrusions, as well as the fault lines that we saw on the last slide. So we have to take that into account, right? We have to make sure that we are paying attention to when those fault lines actually happen, because those are newer than when the rock layers actually formed. So this is an example of intrusion. The magma is actually coming from underneath and coming up out of the earth. That point when it actually comes up out of the earth, like it did in the volcano, is what we call an extrusion. So it's getting a little complicated. We need some hints, we need some clues in our ground that can help us better organize these different layers. So what's a geologist and archaeologists actually use are things called index fossils. These allow geologists to match rock layers, which helps them determine the relative ages of rocks. And two things that they follow is that they must represent species that only live for a short amount of time on Earth, and they were abundant, or there were a lot of them in many locations on Earth. So they weren't here for very long, and there was a lot of them, right? That, and we're going to see in the next slide how that matters. So this image right here is showing us 3 different locations. where we've chopped through the earth, chopped through the cliffside, and we can now see the different layers. I want you to pause the video, think about which one is the index fossil from the ones that you see in this box right here. Alright, so I hope you use the criteria we talked about on the last slide. So what was the first thing? Yep, they should have only lived for a short period of time, and they should be abundant, or there's a lot of them in a lot of different locations. So did we come up with it? If you guessed the ammonites, you are correct. Our ammonites were in all three in that darkish brown layer, and I just covered up that middle one, but it's also over here. Those are actually turns out to be the most widely used index fossils because they were really abundant and they only existed for a short period of time. So scientists kind of use it as a marker to figure out the age of other fossils around it. Alright, so we made it to the end of the lesson. Go ahead and go back to your mission document and start working on the independent practice problems. If you scroll down to page 2, you'll see the step 3 independent practice. You're going to use the 3 diagrams that they give you to date the fossil layers from the oldest to the youngest using the letters of the different layers that they give you. Good luck. I'll talk to y'all later.